Hey everyone, and welcome back to the channel. Today we're diving into a wild story that connects outer space with the ground right beneath our feet. Imagine this. A massive asteroid, bigger than a mountain, hurtling through space and slamming into Earth. We all know this happened, right? Like the one that wiped out the dinosaurs. But what if I told you the impact didn't just stop there? What if the shockwave from that cosmic collision was so powerful it literally shook the entire planet, triggering monster earthquakes thousands of miles away, for days, weeks, or even months after the initial hit? It sounds like something straight out of a disaster movie, but new evidence suggests this might be exactly what happened. So, grab your snacks, get comfortable, and let's explore how a bad day for the dinosaurs was an even worse day for the planet itself. To understand this, we need to talk about the Chicxulub crater. Say it with me. Chicxulub. It's a bit of a mouthful. This is the ground zero of the asteroid impact that occurred about 66 million years ago. It's buried beneath the Yucatan Peninsula in Mexico, and it's massive. Over 180 kilometers, or 110 miles wide. Scientists have been studying this crater for decades, trying to piece together the puzzle of what happened on that fateful day. We know the impact threw massive amounts of dust and debris into the atmosphere, blocking out the sun, causing a global winter, and leading to the mass extinction of about 75% of life on Earth, including our famous non-avian dinosaur friends. But the story gets even crazier. Geologists recently started looking at something they call seismic energy. Think of it like this. When you drop a bowling ball into a swimming pool, it doesn't just make a splash where it lands. It creates ripples that travel all the way to the edges of the pool. The Chicxulub impact was like dropping a planet-sized bowling ball. The energy released was almost unimaginable, estimated to be about 10 billion times more powerful than the atomic bomb dropped on Hiroshima. That's a staggering amount of force. This energy didn't just stay in Mexico. It had to go somewhere. It traveled through the Earth's crust as seismic waves, the same kind of waves that cause earthquakes. So how do we know this triggered earthquakes far away? This is where the detective work comes in. Scientists have been studying ancient rock layers from all around the world, from places as far-flung as Colombia, New Zealand, and even deep under the ocean. They've discovered some very peculiar things in rock layers that date back to precisely 66 million years ago. They found evidence of what's called soft-sediment deformation. Imagine layers of wet sand and mud at the bottom of the ocean. They're usually flat and neatly stacked. But in these specific layers, the sediment is all jumbled up, folded, and fractured. It looks like someone violently shook a giant jar of sand and water. This is a classic sign of intense ground shaking. In other words, a massive earthquake. The key piece of evidence is the timing. These disturbed layers are found just above the KPG boundary, which is the thin layer of iridium-rich clay that marks the exact moment of the asteroid impact. Iridium is an element that's rare on Earth's surface but common in asteroids, so this layer is like a global fingerprint of the event. The fact that the jumbled-up, earthquake-damaged sediments are found right on top of this layer means the shaking happened immediately after the impact. This wasn't a coincidence, it was a direct consequence. The impact was the trigger. Let's put this into perspective. We're talking about earthquakes with a magnitude potentially greater than 11 on the Richter scale. The biggest earthquake ever recorded by modern instruments was a magnitude 9.5 in Chile in 1960. The energy from a magnitude 11 quake would be hundreds of times greater than that. It's an energy level that we, as humans, have never experienced. This superquake wasn't a single event either. The seismic waves from the Chicxulub impact would have bounced around inside the Earth, crisscrossing and reinforcing each other. The planet would have been ringing like a bell for a very, very long time. This new evidence comes from analyzing core samples drilled from deep beneath the ocean floor. One recent study looked at cores from the Tasman Sea, halfway around the world from the impact site in Mexico. Even there, they found clear signs of intense shaking right at the KPG boundary. The sediment layers were completely liquefied and churned up. This tells us the seismic energy from the impact was truly a global phenomenon. It wasn't just a local or regional problem. The entire planet felt it, and felt it violently. So what does this all mean for our understanding of ancient Earth? It paints a much more chaotic and destructive picture of a mass extinction event. It wasn't just about the immediate blast or the long, dark winter that followed. It was also about the planet itself being torn apart from the inside. Imagine tsunamis hundreds of meters high, not just from the initial splash, but also triggered by these worldwide underwater landslides and earthquakes. Imagine volcanoes, already unstable, being pushed over the edge by the intense shaking, erupting and spewing even more ash into the tortured atmosphere. The ecosystem was hit by a devastating 1-2-3 punch: the initial impact, the subsequent global winter, and a worldwide series of catastrophic earthquakes and tsunamis. This also forces us to rethink how planetary bodies interact. We often think of asteroid impacts as a surface-level event. An object hits, makes a crater, and that's the end of the story. But this research shows that the effects are much, much deeper. A major impact can fundamentally interact with a planet's geology, waking up its inner demons, so to speak. It's a profound connection between the cosmos and the geophysics of a planet. This is hugely important not just for understanding Earth's history, but also for studying other planets like Mars or moons like Europa. If we see evidence of ancient impacts on Mars, we should now also look for signs of ancient, impact-triggered quakes. This research is ongoing, of course. Scientists are continuing to drill for more deep-sea cores and analyze more rock formations around the globe. They are trying to build a more detailed map of this ancient seismic chaos and use computer models to simulate exactly how the energy traveled through the Earth. Every new piece of data helps us refine the story and understand the sheer scale of the devastation. It is a testament to how we can use tiny clues locked in stone to reconstruct apocalyptic events that happened millions of years ago. So, the next time you think about the dinosaurs' extinction, remember it was more than just a big rock from space. It was a chain reaction of disasters. The impact was just the beginning. It set off a global seismic storm that shook the world to its very core, leaving scars in the rock that we are only just beginning to read. It's a humbling reminder of the immense power of the universe and how our planet's history has been shaped by violent events on a scale we can barely comprehend. Thanks so much for hanging out and exploring this incredible story with me today. It's amazing what we can learn about our planet's past, right? If you found this as fascinating as I did, please give this video a thumbs up, and don't forget to subscribe and hit that notification bell so you won't miss our next deep dive into the wonders of science. Got any questions or ideas for another topic? Drop them in the comments below. Stay curious, and I'll see you in the next video. Bye.